I just want to finish today's lecture by collecting some kind of random thoughts on scattering parameters. The first is that a lot of times we don't have to go through all the trouble of calculating 4 different scattering parameters. If you were paying attention in the examples in class today, we saw that the scattering parameters were the same in both directions. And that is often the case. In fact, for all passive networks, we have this case that some of the scattering parameters are going to be the same. And if the network is totally passive, we can make the observation that S21 is going to always equal S12. And more formally, this is written in matrix form, that passive networks are reciprocal networks. S is equal to the transpose of S. So here it is written in matrix form for those of you who like matrix math. The useful result is this right here. So this property of a network is called reciprocity, or sometimes people call it as a reciprocal network. And any 2-port network that is totally passive, meaning it's got no active devices, no transformers in it, it will be a reciprocal network. And you therefore don't have to calculate both S21 and S12. You can just calculate one of them, and you will know that the other is the same value. The other way that you may want to utilize the test for reciprocity is you'll look at the 2 matrices and you'll determine is this matrix the transpose of that matrix, and if they are, then the network is reciprocal. So you can also use it as a test for reciprocity. So we briefly mentioned this concept of return loss when we were looking at the S parameters, and we gave them names. And I'm just going to spend a couple seconds going over these. Return loss, it's the power that was in the signal that's returned to the source due to a mismatch. For a perfectly matched system where the reflection coefficient is 0, the return loss is going to be infinity. If a port is completely mismatched, then all of the signal is going to be returned, and the return loss will be 0 dBm. So let me just summarize that. So the case is perfect match, and then return loss is infinity, and that's due to the fact that the reflection coefficient in a perfectly matched system is equal to 0. And in the case for a complete mismatch, the return loss is 0. And these are in dB. And that's for the case that the reflection coefficient is equal to 1, which is a complete mismatch. And consequently, what we see is that we're trying to get power into the load. So return loss, we want a high value. We want the return loss to be infinity dB. Now that's never achievable, right? In reality, we can't ever actually achieve a perfect match at all frequencies. So we want as high as return loss across all frequencies as possible. The calculation for return loss is very simple. It's based on the incident voltage wave to the reflected voltage wave at port 1 here, and you just take minus 20 the log of that, and that'll give it to you in dB. So that's minus 20 the log of the S11 parameter, which is the same thing as minus 20 the log of the reflection coefficient. So by now that should make a whole lot of sense to you, so I'm not going to spend too much time on it. The other parameter that we talked briefly about was insertion loss. And insertion loss is the loss in power due to the insertion of a device. So the insertion loss defines how much of a signal is lost as it goes from port J to port I. In other words, it's a measure of the attenuation that results from inserting a circuit into a network. So with insertion loss, a small value is generally desired. So unlike attenuation loss. We typically want insertion loss. It's good to be small. And the calculation for insertion loss is minus 20 log of the output port reflected wave, the output to the input port. And that turns out that in S parameters, that's just minus 20 log of S21 in dB. Let's finish our discussion on return and our brief discussion on return and insertion loss by doing an example. We've got a network. It's characterized by the given S parameters, and it's connected to a 50 ohm impedance. We want to determine the insertion loss and the return loss for both directions. So we've got 50 ohms of T-line on either side of our S parameter matrix, this network here, this two-port network. And these are 50 ohm T-lines. And we want to know the return loss for if we're headed in that direction and if we're headed in that direction, and consequently the insertion loss for both directions. So return loss 1, that's going to be equal to how much reflection occurs if this is the sending port. And that's going to be minus 20 times the log of the absolute value of the reflection coefficient at the input, which is the S11 parameter. And so that's going to be minus 20 log of 0. And so that gives us a return loss of infinity. No signal dB. No signal is returned. So that's good. In that direction, no signal is reflected. What about if this was the input port and we were going that direction? So return loss 2 in that case is going to be minus 20 log of the reflection coefficient at this boundary, which was S22. And so that's going to be minus 20 log of minus 1/4. And that gives us minus 12 dB. So there is there is a bit of return loss if this is the input port. Now let's look at insertion loss. Insertion loss, if we're going from port 1 to port 2, the insertion loss is IL21. It's going to be minus 20 times the log of S21, which is the power that makes it to port 2 from port 1. And that is going to be equal to minus 20 log of 1/2. And so that's going to be 6 dB of insertion loss. And then IL12 is going to be minus 20 log of S12, which is also minus 20 log of 1/2. That's equal to 6 dB. So didn't have to do that second calculation. We can see that the network is reciprocal, which means that the insertion loss is going to be the same in both directions. I'm not going to go over this. I'm just giving you this chart and pointing it out. It's relatively simple to convert between transmission line parameters and scattering parameters. These are easy to measure. These are not as easy to measure. So typically we use a VNA to measure these, and we'll just use this table of conversions to go from S to ABCDs or from ABCDs to S as shown on the bottom of the chart. So I'm not going to go over any of those conversions. It's just basic algebraic manipulation. You'll practice some in the homework, so I'm not going to do an example here.